Here's a problem from the AP Level C exam from 1984, problem number 2, and it's about satellite motion. You can see a satellite with a mass of 3m orbiting in a clockwise direction, and another mass of m orbiting counterclockwise with the same speed, and they orbit with a radius of 2 times the radius of the Earth, so lowercase r is equal to 2 times capital R. These two satellites collide and stick together, so not only is this a problem of satellite motion, but also conservation of momentum. And we have 3 questions to answer. Calculate what that orbital speed is that each of the satellites have. If they collide, find the final speed after the collision. And then the last part is find the total mechanical energy after the collision. So let's do part A. This should be very straightforward. For a satellite that orbits in a circular path, which describes both of these satellites, the centripetal force is provided by the force of gravity. So mv squared over r equals gmm over r squared. And the mass of the satellite cancels out, so it doesn't matter whether we're talking about the satellite with the mass of 3m or the satellite with the mass of m, because they both orbit with the same radius. They should both have the same speed. And cancel out one of the r's, and we get the familiar result we've seen a lot in this unit of study, that orbital speed for a satellite that follows a circular track is gm over r. We've got to answer in terms of the variables given, so I suppose this means it's, well, here, they've named this as v naught, okay? G, and I guess by capital M we mean capital M subscript E, the mass of the Earth, and then R, the orbital radius, is 2 Earth radii. So this is square root of G, mass of the Earth, over 2 radius of the Earth. There we go. Okay, part 2, or part B, we have to find the final speed if they collide and stick together. So a mass of 3m traveling in one direction, and a mass of m in the same speed going the opposite direction. We'll say initial momentum equals final momentum. So a mass of 3m moving with a speed v naught plus a mass of m with a speed negative v naught. That's the initial momentum. So the final momentum, since they stick together, you have a total mass of 4m, and then it's traveling with a speed v we have to solve for. So the left side of the equation is 2mv naught equals 4mv, cancel out the m, and the final velocity v is just 1/2 the initial velocity. However, we just found that that initial velocity is the square root of gm over 2 capital R. And we can rewrite 1/2 as the square root of 1/4. So we can put this all together in one square root sign and get final speed is square root of g me over 8 re. Maybe it's good enough just to answer in this form, but we're actually going to need it in this form to do part C. Let's read again what part C is. Calculate the total mechanical energy of the system immediately after the collision. Okay. So I'm going to assume immediately after the collision, because the speed changes, the speed reduces to 1/2 the initial value, that in the long term they're not going to maintain this same orbital radius. But in the moment immediately after the collision, that's their distance from the Earth. In any case, mechanical energy is nothing more than the sum of kinetic and potential. I'll just call it E. So E equals 1/2 mv squared plus negative gmm over r. This means E equals 1/2 m times the square root of gm over 8r, right? Just substituting in our answer from the last part. But then all that is squared, so we're taking the square root and then squaring it, so that'll simplify a bit. Minus, let's see, gmm over 2re. Orbital radius is 2 times the Earth radius. Okay, but then we need to substitute for m as well, don't we? This lowercase m is actually 4m, correct? The 3m and the m hit and stick together to give us 4m. So when we plug this all in, we get E equals 1/2 times 4m times G big M over 8 capital R minus G times 4m times capital M over 2R. Okay, so we've got, let's see, 1/2 and 4 gives us 2, and then 2 over 8 gives us 1/4. So we've got total mechanical energy is G M divided by 4RE. Minus, I guess we have minus 2G MM over RE. So we need to get a common denominator. Let's see, how about we change this to, instead of 2 over 1, we change it to 8 over 4. So we've got 1/4 minus 8/4. So we get a total energy equal to negative 7/4 G MM over RE. Okay, that should do it. Thanks.